No,
It makes you
indeed.
feel better. I was just about to remind you.
Thank you. I appreciate that. Good. Thank you. Okay, so it is time to start class. What I want to do is give a broad overview of what kind of where we are and what we're headed towards. So we're working with sets, section 2.1. And can someone remind me of some of the constructions that we did with sets last time? Or at least one construction with sets that we did last time. One important construction that we did with sets last time was we talked about the power set of a set. And this was in context of subsets of a set. And then we had a really confusing, and proper subset. Yes, very good. So empty set and cardinality. Oh, great. Y'all are excellent. Right. So we talked about subsets of a set, proper subsets of a set, cardinality, and the empty set, which is an extremely important set. And then we started talking about power sets of a set, and I think I did some confusing examples about the empty set. So I want to do some more examples about power sets with something a little less challenging than the empty set first. Does that sound reasonable? Okay, but in any case, where we're going to go after this, we're going to work on power sets a little bit more. Then we're going to do Cartesian products. And then we're going to move on into section 2.2, which will have unions and intersections and stuff like that. So when we get into unions and intersections, these are going to be new ways of creating new sets from old sets. We're kind of already doing that over here with power sets and Cartesian products, though. Okay, now that we've kind of surveyed the area of what we've been talking about for the past day, does anyone have any questions before I go forward? Okay, let's do another power set problem. I think what I want for us to compute is a slightly easier power set problem. I want to compute the power set of the set containing 1. And we're going to do it in steps. So if I want to find the power set of the set containing 1 element, namely 1, then the first thing that I should do is I should just find the power set of 1. So here, on this side, we need to find all the subsets of this set. What's always going to be a subset of any set? Yep, we always have the empty set as a subset of any arbitrary set that we have. So we know that the empty set, will be an element in the power set of this set. What's another subset of this 1 element set? That's right, 1, the whole thing. This thing is also a subset of this set. Those are 2 that you always get for free. Anytime that you're thinking about subsets, you always get the empty set and you always get the whole thing. And in this case, there's nothing else, right? There's no other possible subset of this set. So the power set of this set containing 1 is going to be a set whose elements are sets, and 1 element is the empty set, another element is the set containing 1. I think at this step, we're probably okay, right? This is at least a little less confusing than when I was playing those games with a bunch of brackets around empty sets. So a power set of a set can only contain sets. That's right. So by definition, the elements in a power set are subsets of the given set. Right, so 1 is not a part of this because 1 is an element of the set containing 1, but is 1 a subset of the set containing 1? No, it is not. But I do have 1 as a subset of 1. Right. So the set containing 1 is a subset, and therefore it is an element of the power set. Your questions are excellent, by the way. Please keep asking them. If there's any more I can explain about this particular example, I would be very happy to.
I have a quick question.
Yeah, sure.
Why can you write the empty set as an element of the power set instead of a subset?
Well, that's a great question. So is the empty set an element inside the set 1? Remember, what does it mean to be an element? What are the elements of this set?
The empty set in 1?
Actually, it's only 1. The empty set is not an element in here. The elements are like the objects that the set contains. But this doesn't contain the object, the empty set. It's just that a subset of a viable subset of the set is the empty set. But 1 is the only element inside this set. So the empty
Okay,
set is
makes
not
sense.
an element in here.
Okay, I'm following.
Let me just really check what this question again was. So a power set of a set can only contain sets. That's right. Yeah, that's absolutely correct. Because by definition, the elements of a power set are the subsets of the set in question. So it's kind of like Inception, right? You go another layer deeper, where if I take another power set of this thing, then I'm going to have sets of sets, but these are already sets which are subsets of the original set. What I just said is more confusing than actually just doing it. So to find the power set of the set containing 1, what this next means is I want to find the power set of this set. Okay, so now we're going to ask the same questions. Now for this new set, first of all, how many elements are in this set?
2.
Right, there are 2 elements in this set. The empty set is an element. Here, the empty set is an element, but it's not the case here, right? The empty set is an element, and the set 1 is an element here. Yeah, so there are 2 elements here. Now we are going to ask, what are the subsets here? Okay. So when we think about subsets, what 2 things are always there?
The empty set and the set itself.
That's right. The empty set is also a subset of this set, right? The empty set here is also a subset of the set containing the elements, the empty set and 1, because the empty set is always a subset. What else is a subset that we get for free? Yes, the empty set in itself. So another thing that goes in here is the set itself. The empty set, the set containing 1, that goes in because the set containing the empty set and the set 1 is certainly a subset of the set containing the empty set and 1. Sorry, you can't really see. There we go. Okay. Now there are now 2 additional proper subsets. Well, yeah, 2 non-empty proper subsets of this 2-element set that correspond to choosing one of the 2 elements, right? I think of making power sets as ways that you can choose some elements from the set. The empty set corresponding to choosing no elements. If I find these 2 in the fridge, then the empty set means, oh, I'm not hungry actually. The full set means I find these 2 in the fridge and I eat both of them because I'm starving. But then the other options are, oh, I could take one of these from the fridge, right? The set containing the empty set is a subset of the set which contains the empty set and also something else. And I could also take the set containing the element 1, because this is a subset. And how do I check? If I want to see that this is a subset of this, I open up the set. I say, what are the elements in this set? The only element is the set containing 1, and since the set containing 1 is in here and the set containing 1 is in here, this is a subset. So it goes into. How are we doing with this?
But I just have a question about the 1. Why wouldn't it not have just one set of the accolades, the brackets thingies?
Well, because when you have one set of, so remember that the set containing 1 is an element. That's what this thing right here is describing. The set containing 1 is an element in this set. So maybe I can do some other exercises that are kind of nearby. So for instance, is 1 an element inside the set containing the empty set and 1?
No.
This is false, right? How about the set containing 1? Well, sorry, this is kind of repeating myself. This one is, right? So let's transpose to a different scenario. If A is inside the set A, B, C, does that mean that A is a subset of A, B, C?
It's just an element, right? So it's not
It's just an element, it's not a subset, but I can make a subset by taking the set containing A. This is a subset of A, B, C, right? Because when I open up the set and I look at the element inside, it's in here and it's also in here. Is this okay?
Yeah, and the same thing you did with the 1, right?
And that's exactly what I did with the 1.
Mm-hmm.
I need to put additional, I need to take the set containing the element, and where the element is the set containing 1. And this is precisely that thing. Yeah, exactly, Morgan. This is the correct idea. So if I have an element inside a set, then to make a subset from the element, I put brackets around it. And that's exactly what happened here. This object, the set containing 1, was an element here. So to make a subset, I took the set containing precisely that element, the set containing 1. And this is a subset here. Any questions here? Would we do anything else for the first example with the 2 P's? No, this is a viable answer. Once you compute what the power set of the inner thing is, and then you compute the power set of that, then this is the answer for the power set of the power set of the set containing 1. That's fine. Yep. And so I think that once you know how to do this, and once you see how this works, then our example last time where we were doing like the power set of the power set of the power set of the empty set becomes more clear, because what happens at the first step is the power set of the empty set. Can anyone remind me what the power set of the empty set is? What are the subsets of the empty set? Right. The empty set is the only subset of the empty set. By the way, Morgan, you use some dangerous notation in the chat, because the set, what you wrote there looks like the set containing 0. A better notation, if you're typing for the empty set, would be this, right? You want to ensure that you're not having oh, I see what you mean. But yes, so the power set of the empty set is the set containing the empty set. But a more appropriate way to type that, I think, would be this. Or, I don't know, something like this. When you're like playing with brackets, this is a set containing the empty set. So brackets containing nothing are a reasonable way to denote the empty set. Okay, but in any case, the point is, this is just a set with one element, right? It's just a set with one element, and that element is the set, which is called the empty set. If I want to do the power set of this, it's exactly the same as doing the power set. Like if I want to take power sets of this, this looks identical to the set containing 1. I just have to remember everywhere where I have set containing var nothing, or the empty set in my calculation, I have to go and replace it with copies of the empty set. So this calculation, if you replace all the 1s with the empty set, will precisely give you the power set of the power set of the empty set. So working out things with the set containing the element 1 might be an easier way to kind of look back on power sets of the empty set and stuff like that. Is this okay? Both of these sets just have one element. And so their power sets should look pretty similar, just with a renaming of that element. Any questions? We're okay with power sets, or at least we're okay up to some homework. Of course, we need to practice, but great. And then lastly, I just have some brief exercises that probably will be easy after all this discussion for y'all to help me out with. These are just kind of some games here. So tell me true or false with the following propositions. So what's going on here? I'm asking if the empty set is an element of the set which contains the empty set. Yeah, this one's true. The empty set is indeed an element, because what are the objects of this set? Well, this set has one object, and it's the empty set. This is my folder inside a folder, and then there's nothing inside the inner folder. Okay, great. How about, is the empty set an element inside the set containing the empty set and the set containing the empty set? Yeah, this one's true as well. This object appears as an object of the set. Great. How about, is the set containing the empty set an element of the set containing the empty set? Correct. I love seeing all the F's in chat. This is false. It is true that the empty set is an element in here, but it's not the case that this set contains an element which is the set containing the empty set, right? There are a couple things that I could change to make this a true statement. What are some of the things that could change?
Say that it's a subset.
I could say that it's a subset, absolutely. This is indeed a subset of this set, because to check subsets, I find out what the elements in this set are, and there are exactly, the empty set is the only element in this set, and the empty set is indeed an element of this set, so we have subsets here. Also a great point, Catherine, we could also add brackets. So here's another true statement. The set containing the empty set is an element in the set whose object is, say, well, let me do something to make it non-trivial. So this is a true statement. The set containing the empty set is an element inside this set, because I found it right here. One last example, which is what people are writing, is that this is an element in the set just containing the empty set. Or the set containing the empty set, right? Now this is an element here. And it's for the exact same reasons that this was an element here, I've just forgotten about the other element, right? So this is true, this is true, and this is true. Any questions here, or are you now feeling kind of comfortable about these distinctions between subsets and elements? One more false example. Yeah, sure. Let's see. What's a good false example? How about this one? Let me see if I can pull off a good false example. The empty set and the set containing the empty set is a subset of this. Here's false. Here, tell me why this is false. First question, what are the elements of this set? Yeah, that's correct. There are two elements in here. One is the empty set, and the other is the set containing the empty set. What are the elements of this set?
The set containing the empty set.
The set containing the empty set. In order for this to be a subset of this, all of its elements must be elements over here. But in fact, neither of its elements are elements here. Right? The empty set is not an element, and the set containing the empty set is not an element. Does this help with the false example?
How is the empty set not an element?
So what I have done here is I have listed all of the elements of the set. The objects that I write that are inside the braces are the objects. So this is the object. I should not do squiggly things. This is the only object inside this set. And this set, the set called the empty set, is not an object simply because it doesn't appear on the list. The empty set is a subset of this set, but it's not an object in this set. Maybe if I gave names to things, this would be a little bit better. Like, let's say that I wrote the empty set and I did the set containing the element A. And I ask, is this a subset of the set containing the element A? I can also do this. Backwards, it would not be true. And I'll get to that in just a moment. So here, what are the elements? Here, the elements are the empty set and the set containing A. This is my list of elements. Here, my list of elements is the set containing A. In order for a subset relation to hold, everything on this list must also be on this list. But in fact, nothing on this list is on this list.
I think I'm confused on why the empty set isn't on the list on the right.
Yeah, so the fundamental thing is that here, the empty set is being treated as an element. So here's something that is true. The empty set is a subset of the set containing the element A. This is true. But when I treat it as an element, and here it is an element, right? Because here the objects inside this set are themselves sets. And here, the element called the empty set does not appear on this list. Here's a way to partially repair this. The empty set, the set containing A. And I could ask, is this a subset of the set containing the empty set and the set A? Now the empty set is listed as an element in both. So here my list of elements is the empty set and the set containing A. And here my list of elements is the empty set and the set containing A. I still don't have an inclusion because this element isn't in this list. But now I've repaired the fact that the empty set, considered as an element, is in both.
Okay, that makes a lot more sense now. Thank you.
Does this help? Okay. Let's go back to Alex's question. So let's now ask, does the reverse hold? The set containing A, is this a subset of the set containing the empty set and the set containing A? Okay, what is the only element in this set?
Set containing A.
Yep, the set containing A is the only object on my list of elements here. What are the objects on the list of objects for this set? Yep, the empty set and the set containing A. But as objects, these are different. So this is not a subset because there's an object here, which is not an object over here. The relationship between the set containing A and the set containing A is that this object is a subset of this set, but when I'm treating both of them as objects, they're not the same. When I'm computing subsets, I just make lists of elements and I say, is every element here over here as well on this list? And this symbol, if you will, is not on this list of symbols, so that we don't have a subset relation. Does that help answer your question, Alex? Right. This could be repaired by asking, is the set containing the set containing A an element of the set containing the empty set and the set containing the set containing A? Here the answer is yes. Look, I found it. This is an element here. I have taken one of the elements of this set, taken it out and said, are you in the set? And the answer is yes. Okay, so are we starting to kind of untangle these relationships between elements and sets and subsets? Great, yeah. This is surprisingly challenging stuff, and it takes time and it takes practice, and it requires some effort to realize kind of what we're doing. But it can be interesting. Any further questions? Exactly. Got to count those brackets. All right. I'm personally ready to move on to Cartesian products. How about y'all?
Sounds invigorating.
I agree. I agree. Cartesian products. Okay, what we need to do first is get a definition. There are going to be a lot of definitions coming in the next couple days. So just be, on the lookout. Reading ahead can be helpful perhaps here. So an ordered n-tuple. First, I need to talk about what an ordered n-tuple is. And it's going to be written as essentially just a list, A1 all the way up to AN. So there are n elements that are appearing in this tuple. Is the ordered collection that has A1 in the first position, etc. So two ordered n tuples are the same if they have the same elements in each position. Okay. This is not an unreasonable definition. All I'm saying is that an ordered n-tuple is a ordered list, and in each slot, so to speak, is a set element. And in this case, the order matters. So if I made an ordered n-tuple of elephant and 3, I would not consider this to be the same as the ordered n-tuple 3 and elephant. Fairly reasonable, I think. We're counting order now. Order matters in this setting. Okay, definition. The Cartesian product of two sets. So let A and B be sets. The Cartesian product of A and B, written A cross B, or the product of A and B, is the set of all ordered pairs A and B such that A is in A and B is in B. Okay, lots of writing, but more formally, or more using more more symbols. Indeed, it's exactly a cross product. Well, it's not a cross product of vectors. It's a cross product of sets, but you'll know that you're also familiar with this. Cross products of vectors or cross products of sets? Well, you probably can't escape either of them. Okay, so this is a pretty reasonable thing. You're given two sets, and you make a new set out of both of those sets by looking at the order in which those sets are given, A and B. So here A comes first and B comes second. And then you make the new set, which consists of all ordered pairs, such that the first term comes from A and the second term comes from B. How are we doing on this definition?
What does the line after the ordered pairs mean? Yeah, right there.
In set builder notation, this is how I specify conditions. So I'm looking at all ordered pairs, okay, and then the line would be how I say, I only want such ordered pairs. So for instance, if I was trying to write the set of all odd numbers, I could write odds equal the set of x in z. Okay, but I certainly don't want all of the integers, right? I want such that, this is some condition, such that x is equal to 2k plus 1 for some k in z. So here is where I put a condition on which elements I take from the bigger set. Does that help?
Yes.
Great. Let's do some examples. Examples are the best. What is the cross product of the set 1, 2, 3? And I'm not going to do A, B, C, despite that being visibly superior, but I'll just do A and B. So what is the cross product of these two sets? Well, it's the set of all ordered tuples, right? Ordered pairs. What is one element in the cross product? Yeah, 1A is a perfectly good element. 1A is in here. What's another one? Yeah, 2A. What's another one? Yeah, 1B. That's good. What else? I'm going to make y'all list all of them. Unfortunately, you listen to too much Michael Jackson, Jackson 5. C is not involved here. Got him. No, so C doesn't play a role here, but 3A is here. Great. Also 2B and also 2C. Okay. Oh, shoot. Oh, man, now it's on me. 3B is the correct answer. I blame myself. I'm responsible. A self-got 'em, if you will. Okay, this is reasonable, right? This is more or less what we expected would come out of this cross product. Is that okay? For a more immediately acceptable or familiar example, let's talk about the Cartesian plane. R cross R, Cartesian plane. What's an element in R cross R? Yeah, it's the set of all ordered pairs of real numbers, right? So I can, for instance, take 1, 0 inside this Cartesian product, this is a perfectly fine element. And moreover, there's a nice way of looking at this cross product. This would essentially be, I go a 1 along this axis and I go a 0 along the other axis. Right? If I wanted to go 3, 5, I can represent this ordered pair as going over here, 3, 1, 2, 3, 4, 5, going all the way. Oh man. Let's do 1, 5 instead. 1, 5 is this, it can be represented graphically as this element. So the Cartesian plane that you're very familiar and comfortable with can be described as a set as precisely the Cartesian product of R and R. Okay? Yeah, right. Everything is everything is unified. Everything is mathematics is one, as one of my favorite professors says. Right? As a set, the Cartesian plane is precisely the Cartesian product of the two parameters that you're dealing with. That's kind of nice. Any questions on this so far?
So is the definition of the Cartesian plane just all real numbers by all real numbers?
As a set, the Cartesian plane is precisely R cross R. And to specify any element of this set, you specify two real numbers in order, right? So in particular, this point 1, 0, we know is different from the point 0, 1 because they're ordered tuples. And indeed, they look different, or you can see that they're different points or elements of this set kind of graphically if you want to think about this set graphically. I'm not sure I answered your question though. Did that help?
Yeah, I think it did.
Yeah, the answer is essentially yes. What you think of as the real plane, the 2x2 real plane, is described as a set as the Cartesian product of R and R. Of course, this is just a set, right? R cross R. I mean, it's a set that we built out of other sets, but it's just a set. Do we agree? I can also, if I wish, form the Cartesian product R cross R cross R. What are going to be the elements of this set? Well, I've got some set here. I'll call this whole set A, and I'll call this set B. So they're very close to ordered triples. I want to make something kind of clear here, though. I want to kind of show something kind of pedantic. So let's consider the two sets R cross R as a set cross R versus R cross R cross R. Okay, technically, so it's going to be these both will give us points in 3 space, but technically, what a point here is, I can think of this as A and then this set B. So an element of set A is an ordered pair. So to specify an element here, I take an ordered pair associated to A and B. I pick any element of B, so like, I don't know, 3. But then what goes in here is not just a pair of numbers. I put in an ordered pair. Yes, precisely. 2, 4, 3. So if you want to think about this as a point in the 3 plane, you think of this as I give a point of the 2 plane, and then I give another point. Over here, things are a little different. Here, a general point looks like A, B comma C. And I want to really emphasize that these are not the same set. These sets are extremely closely related, and both of them will give you points in R cross R cross R, but technically, elements of this set are an element of R cross R followed by an element of R, whereas elements of this set are first an element of R followed by an element of R cross R. So in general, the point is A cross B is not equal to B cross A if A and B are different sets. Are we okay with what I'm doing so far? Do we understand the subtle distinction that I'm bringing up here when I say that these are not the same set? Right. The point is that this is an ordered tuple with the second element coming from R and the first element coming from R cross R. There's no way that any such thing could be the same as something over here where the first coordinate is in R, a totally different set than the first coordinate over here. And the second set is pulling from a totally different set than where this second coordinate is pulling from. Okay, but I want to remark that we can define larger ordered tuples, or larger cross products. Larger Cartesian products is the correct thing I should say. So I can also define R cross R cross R, and here this is genuinely tuples A, B, C. None of these sets are the same. None of these sets are the same. Right? Here, the elements of this set are tuples, ordered tuples. Here, the elements of this set are also ordered tuples. Here, the elements are ordered triples. As we continue in this class, we'll see that there are a bunch of functions in between these that make them all essentially the same if you want to. But for right now, objectively, we need to consider these as different sets. And by the same, I mean they're what I'll call, I suppose, isomorphic as sets. But these are different sets. Okay, we are at 10:09. You may have 1 minute to tell me exciting things that you're going to do with your weekend.
I'm going to study for these 2 exams on October 9th.
Excellent. Sounds like a great use of a weekend. Hiking is great. Crying is great too. They're all, all good ways to get some stress out that I'm sure we're all feeling at this time of year. Hey, congratulations. Sounds like people have some big plans for this weekend. Happy birthday, yeah. All right. I hope that everyone has a wonderful weekend, and I'll see y'all on Monday. Actually, someone will probably be subbing for me on Monday.
Thank you.
Thank you.
Yep. Have a nice weekend, everyone.
Thank you too.
Mm-hmm.